Hello, everyone. I'm Anup. I work with Freiburg Galaxy team in Germany, and I'll be talking to you about clustering today. And I hope all of you are learning something new in the last sessions about regression and clustering uh, and classification as well. Just to recap what we learned so far this week, we discussed lots of techniques for supervised learning, like classification and regression. Let's just recap that. And for supervised learning problems, the data that we use already has defined targets or labels. There are different names of these. You can call them targets or labels or classes or categories. These are defined for supervised learning problems. Basically, there are two categories, classification and regression. Just they differ on the kind of or the nature of the targets. For classification, we have discrete targets. We have different classes. For regression, we have continuous targets. On your right, you can see two images. One is for classification, and another is for regression. For classification, we can see this is the red boundary that we try to learn, which creates a separation between two classes or maybe multiple classes. For regression, we try to derive or we try to learn a curve which may be linear or non-linear through the targets, through continuous value targets. But what will happen if we don't have these targets? Then how do you try to learn from the data? We cannot, right? Because adding these classes to data requires a lot of human effort, which may not be always possible or may not be easy to do, or it may be very costly. For example, let's suppose we have thousands of biomedical data. Each image contains images of tissues, and it's actually very hard to label them if we have like thousands or millions of such images. In order to find categories in these unlabeled data, we actually go towards different solutions which can be categorized under unsupervised learning. This is unsupervised because we don't have any defined categories. There is no teacher. We need to learn the categories from the data itself. There could be different tasks under supervised learning. For example, there could be principal component analysis, where you try to reduce dimensions by learning the very important dimensions in your data. Another could be clustering, where you actually try to find different groups inside the data. Another example could be density estimation. There could be many more. Essentially, we are trying to learn without these targets. On your right, you can see there are two images. One is without any clusters defined inside, and on the rightmost image, we can see lots of clusters, like 3 clusters defined for these. In this talk and the demonstration afterwards, we will see the clustering techniques. There are different types of clustering techniques, and we will go 3 of the clustering techniques and visualize the results, and we'll be able to compare them. Clustering. Clustering is actually grouping samples based on similarities. But what is a similarity? We need to be able to find different mathematical functions or different techniques to find similarity between samples. And then we can say that these two samples are very similar to each other, or these samples are very different from each other. We work on the assumption that the samples which are very close to each other, it means they are very similar to each other. They may have a similar nature. For example, if we are clustering, for example, gene expression profiles, and if we find, say, 5 clusters, and inside each cluster, If some genes are together, if their profiles are together, we can say that they may have similar functions in biological processes. There could be many different measures of similarity. It could be distance from the center of a cluster. It could be distance between two samples, or it could be distance between two nearest neighbor graphs of samples. For each clustering technique, we will have a different similarity technique. We can also change them, and also the result may vary if you use different similarity measures. The applications of clustering could be, for example, in bioinformatics, could be clustering gene expression profiles, which could give us some insight into which genes are functioning in a similar way and which not. For image analysis, it could be helpful in finding segments inside image, for example, identifying objects inside object and then cluster based on the segments inside each image. Broadly, there could be many different types of clustering based on the similarity measures, or how do we try to identify each cluster. Some of the examples could be a connectivity model. In this, distance between samples is taken as a similarity measure. If the samples are very close to each other, then they are very similar. If they are farther, then they are not that similar. One example of connectivity model is hierarchical clustering, where we learn a hierarchy of clusters. The second one could be centroid model. In this, we try to find the mean point or the midpoint of a cluster, of each cluster, and all the samples which fall in the cluster have some kind of similarity. One example of the centroid model could be k-means clustering. Another variant could be k-median clustering or k-centroid clustering. The third example could be density model. In this model, the cluster is actually found by computing the density. If the samples are very close together, then it becomes a cluster itself. One example could be DBSCAN, which is density-based spatial clustering of applications with noise. And there could be many more. The first three, we will be looking at each example of all these clustering in our tutorial as well. And in the talk, I will try to explain the logic behind each of these clustering techniques. Hierarchical clustering can be divided into two types, agglomerative and divisive. We'll be looking at agglomerative today. Agglomerative is actually a bottoms-up approach. What we do in this, let's suppose we have n samples in our data set. Then we assign each sample to its own cluster, and then try to merge the clusters which are close together until until we reach to a one very big cluster. It's called a bottom-up approach because we try to arrange all the samples and then try to build up one cluster. Another approach could be divisive, where we first assign every sample, all samples in one big cluster, and then try to divide it. We'll be also seeing what is a dendrogram. So dendrogram is a kind of plot where we can see these hierarchy of clusters. To see a visual example of hierarchical clustering, let's suppose in the square box we have 8 samples, and each sample has 2 dimensions, dimension 1 and dimension 2. And then on the right, there is a horizontal axis. We have arranged all the samples based on the distance. For example, point number 4 or sample number 4 is closest to point number 2, and then 3, and then 7, and then 5, and so on. And 4 is farthest from sample number 6. Since we try to take one point or one sample and then try to find the nearest sample, In the second image, we see that 2 is the second sample, and we try to merge these two clusters together. Then here we can see these two clusters, 4 and 2, got merged. The height of the distance, this height gives actually the distance between these two samples. Now we try to find, now we have merged this cluster, then we need to find the next closest cluster, which is between 5 and 8. And this height gives the distance between 5 and 8. And on the left, we can see we already find 2 clusters. Then we try to expand it. Then we find 3 joining the cluster of 4 and 2, and so on. And we then try to include 7, and then further we try to include 1 on the right. And then we have created these 2 clusters. And to join these 2 clusters, we can find the distance between this cluster, and then join them. This blue line gives a similarity, like we have 2 clusters here. By these, looking at these dendrograms, we can see how these clusters, hierarchical clustering, is actually working inside, and try to find clusters in the data. The next clustering technique is k-means. As we discussed before, it's a centroid model. In this, we try to find the mean or the midpoint of each cluster. It actually works by minimizing the variances inside each cluster, which means that we try to find a point which is at best the midpoint of all the points inside that cluster. And overall, together, we try to minimize the overall sum of cluster variances. How do we do that? The first step could be, first we choose k centroids or k points. Since we want to divide our n samples into k different clusters, first we try to randomly assign k different points as centroids. Then in the second point, we do a matching. For example, if one sample is closer to one cluster, is closest to one cluster, then that sample becomes a part of that cluster. Then, which can be said in another words, like assign each sample to its nearest centroid. Now, since we have each sample falling into different categories or different clusters, now we can again take the mean of all these points to create new centroids. Since we get new centroids, we again try to find all those samples which are closest to it, and then we take a midpoint again to find new centroids, and this iteration goes on until there is no change of the positions of the centroids, or we can define a threshold. If the change is lower than that threshold, then we stop our algorithm and we say we have already found k clusters. K-means clustering actually assumes that our clusters are convex, which means that in 2D space, it could be circular in nature, or it could be in 3D space, could be spherical in nature, because we try to find the midpoints, which is equidistant from all the samples. This technique is actually not optimal for clusters which are irregular. For example, if the cluster is an elongated or in cylindrical shape or some other irregular shapes, then this clustering is not optimal for that kind of data. It generally converges, but it may converge to a local minimum. The global minimum or the optimal solution is not guaranteed. And to find a local minimum or find a good solution, the initialization of centroids is very important. That's why in scikit-learn implementation of k-means, they try to do, they use some seed points and try to see if these randomly initialized centroids are maximally separated from each other, so that in the end we can get a decent solution in the end. We can see the K-means clustering visually. In the first image, let's assign these 2 points, blue point and red point. I hope you can see those points. This is a blue point and this is a red point, and these are 2 centroids which is randomly assigned. And then in the second point, what we do, we assign each point to one of the centroids or cluster centroids, which is nearest to that point. In this example, we see the red points are nearer to the red centroid, and the blue points are nearer to the blue centroid. In the third example, now we have assigned all the points. Then we can compute the mean of all these points, and then try to find the new centroid positions. We find the new centroid positions, then we again try to assign all the samples to the centroid and get a new centroid positions in the fifth image. And we do that till we find no change or very small change, which is less than a threshold for the centroids. And then we say we converged and found these 2 clusters in our data. Another example of clustering is DBSCAN, which is actually based on computing the density for each cluster. Clusters are actually regions of high density. How does it work? It defines each sample into a core sample and a non-core sample. Core sample is such a sample which has at least n number of samples within m distance. This n and m are actually hyperparameters of this algorithm. I'll try to explain again. A core sample are those samples which make a region of high density, and it should have at least n samples within m distance. M is a float number. It could be 0.3, 0.5, and n is actually an integer. It could be 5 or 10. It means that, for example, if n is 10 and m is, say, 0.5, then we can say that a sample is a core sample only when it has at least 10 samples within 0.5 centimeter of distance. As I said before, n and m are hyperparameters. It can be changed, and it can be different depending on the data set. A non-core sample can also be a part of the cluster, which actually make the boundaries of that cluster. The small circles that you see, these are the non-core samples, and the larger circles that you see, which are more condensed, these are actually core samples. The non-core samples should be within m distance from any core sample. For example, if you take a core sample, this one, then a sample which can be a non-core sample should be within m distance. If we say 0.5 centimeters, then should be within 0.5 centimeters from a core sample. If it is not, then it becomes an outlier, which we can see these black spots that we see. These are actually the outliers, and they do not belong to any cluster. And DBSCAN algorithm in scikit-learn, it assigns for these points -1 value, which means that these are outliers. DBSCAN is actually a good clustering algorithm for clusters if you want to find clusters having similar density. And it also works with arbitrary sizes of clusters. Even if a cluster is elongated or any arbitrary size, it works. we can see a high-level comparison of all these three clustering algorithms. First, hierarchical clustering that we saw, it can have three parameters: number of clusters, and then linkage type and distance. Which kind of distance? For example, Euclidean distance. Linkage type is actually a kind of minimization function of distance that we specify. Scale, how does it scale? It can take a large number of samples and clusters. It can have many clusters because we saw that it can have as many clusters as the number of samples. However, this clustering algorithm may not work for a very large data set. K-means algorithm actually works very well with large data sets, but with a small number of clusters, not with huge number of clusters. And also, it works optimally for data sets having a uniform cluster size. DBSCAN actually needs only neighborhood sizes. For example, we discussed M and N, which is minimum number of samples it needs to have within M distance. These two parameters needs to be set. It can work with very large samples and medium number of clusters. And it also works very well with uneven sizes of clusters. We can summarize this talk. Clustering is actually finding groups, and in each group, we can say that samples are actually similar in some way. They have similar nature. Similar nature means they may have similar functions, and they may contribute in a similar way to some biological processes. There could be different techniques for clustering. For example, hierarchical clustering, which is a connectivity model. Another is K-means, which is a centroid model, and DBSCAN, and there could be many more. Some of these clustering techniques are good for large number of samples. Some are not so good and work with medium size data sets. And all these algorithms have hyperparameters, and optimal setting of these hyperparameters should be found so that we get optimum performance, which varies with different values of these hyperparameters. With this, let's go to the tutorial. Meanwhile, if you have any questions, I can take those questions.
Hi, Anup, it's Prem speaking. Yeah, there are a couple of questions actually coming in through the question box. So I'll just read them out, and you can elaborate on at least on some of them. So this one is from Ramesh, and it's about the clustering technique. Do you set the intercept between the clusters, and on what basis? And there is another question related. How do you choose the number of cluster from the data?
This example we will see in the tutorial. How do we choose different clusters? How many clusters? I'll be explaining them in the tutorial, which will follow soon. And the first question, actually, I didn't understand. Can you?
I think it was referring to one of your early slides where the points in the scatter plot were divided by a line, and I think the intercept meant.
Okay, I guess this one.
Yes. About.
Okay. Okay. So actually, I'll be describing this concept again in the tutorial. So should be answered very soon.
Okay.
Okay.
And
And any other
There
question?
is, yes, this one is more general. How do you
Okay.
deal with outliers?
Uh-huh.
So this is doesn't refer to any specific algorithm that you described, but in general in for clustering techniques.
Okay. So as we discussed, k-means algorithm is not good for handling the outliers. So to have a better solution, we can use k-medians, which are actually better at handling outliers. The second approach we can use is DBSCAN. DBSCAN takes care of these outliers very well compared to other approaches. I think currently I can say only these two possible solutions.
Okay, so maybe we can move on to another question,
Mhm.
if we still have time. Uh,
Yeah,
is
yeah.
it possible to predict the number of clusters from the dataset without explicitly setting it manually?
So in DBSCAN, we saw that it actually learns the clusters based on the data. We do not specify the number of clusters. So in that case, if we are not sure about the number of clusters, it can happen. We can use DBSCAN and see what kind of clusters it produces, because there we don't need to provide any number of clusters.
Okay, let's move. So we have actually two more questions, and then maybe we can continue with the presentation.
Mhm.
So, in terms of complexity, time
Mhm.
and space, which algorithm is better? Any suggestions how to choose between
So
them?
yes, so hierarchical clustering is actually the optimal version of hierarchical clustering is actually quadratic. It's O of n squared. That's why I also discussed that it may not be a good choice of clustering technique for very large data sets, because it has higher time complexity. But on the other hand, k-means clustering has a complexity. One variant of k-means clustering has a variant, and uh, its its time complexity is linear in terms of number of samples and number of clusters. I'll be actually talking about this clustering time complexity again in the tutorial. I guess it will be more clear there. We have a section in the tutorial.
Okay, so let's do one more questions and then continue with the
Yeah,
presentation. So
yeah.
for RNA-seq, which type of clustering is preferred? Do we use complete gene set or the top 100 different expression genes for clustering?
Um, I'm sorry, but I don't have answer to this question currently.
Okay, so
Okay.
we'll keep the questions in the list, and we'll answer it in writing. And then I think now we can move on with the presentation.
Yeah. Okay, let's go to the tutorial. First, we should go to the training website. In this, we should scroll down and please find statistics and machine learning section. Let's go inside this section, and then we can click on clustering and machine learning. The clustering can also be divided based on the assignment of data points. It's a very broad classification. It could be hard clustering, and soft clustering. Hard clustering is when we assign each data point to exactly one cluster, then it's hard clustering. One example is k-means or DBSCAN. Soft clustering is actually when we learn probability or likelihood of being in a cluster. For example, if we have 3 clusters and few samples, then for each sample, we will have a probability distribution. For example, each data point can have 70% probability of being in cluster 1 and 20% in cluster 2 and 10% in cluster 3. One example of this kind of soft clustering is expectation maximization algorithm. We already discussed a few types of clustering techniques or models, connectivity model, centroid model, and density model. We will go through one example each of these types of clustering models. We will be actually using iris flower dataset. Iris is a flower, and it has different features. For example, sepals and petals. This dataset describes sepal length and width and petal length and width. And based on these 4 features, we will try to find the clusters. But before that, let's have a small example how we can see which samples are closer, which samples are not. In this section, we can see a count matrix here. Count matrix has on rows is the genes defined, or we can say features, and then on the rows we have all the cell types, and then we in this count matrix we define all the counts of the features. Each of these cell types will have a vector which is shown vertically, for example R, P, and V. To translate this count matrix to distance matrix, we can use a distance formula. For example, we can find a Euclidean distance between each point or each cell type. We can use the distance feature and compute, for example, distance between a cell type R and P, and then we come up with root over 13, and then we create this distance matrix, and between R and P we place this value. And similarly, we compute all all versus all combinations, and then end up with this distance matrix. Just by looking at this distance matrix, we can say that the point P and V are closer than P is with R, because P and R, they have a distance, or they have a higher distance compared to P with V. Based on this distance matrix, we can say that PV are more similar than P and R. This is the basic principle how the clustering is actually made using any distance function. There are a few questions. We can try to answer them. There are zeros in this matrix because distance width itself is actually 0. And this matrix is symmetric because R with P and P with R, it's the same distance. In addition to using distance functions, we can also use correlation functions. For example, Pearson correlation or Spearman correlation to find similarities between samples. When they are highly correlated, then then 2 samples are similar. And when they are not correlated, they are uncorrelated, then the similarity is low. Pearson correlation is actually does not take into account outliers. To overcome that problem, we can use Spearman correlation, for instance. We will see different clustering approaches. First of all is hierarchical clustering. We saw that how we can create these dendrograms using a bottom-up approach. We specify all the samples based on the distance and try to merge the clusters together until we get a big one. To answer to the question, how many clusters how many clusters we need to specify. For example, looking at the data set, we cannot say that how many clusters we can specify. We can try to build, for hierarchical clustering, we can try to build this dendrogram. And with this dendrogram, we can actually try to find optimal number of clusters. The, the principle behind finding the optimal number of clusters, looking at the dendrogram, is we should actually try to draw a horizontal line. Let's say the horizontal line A, and try to find and try to roll it down until it reaches another cluster, and try to compute these distances without intersecting any other cluster in between. For example, we start with these 4 clusters here, which got traversed by the horizontal red line A, and we try to pull it down until we reach this point just before these 2 clusters. If we try to find this distance any other place, we will not find any distance larger than this. Then we can actually count how many vertical lines we have intersected, and these count of vertical lines actually give the number of clusters. We can read here in this paragraph, which explains this technique. So based on this, we can actually find the optimal number of clusters for hierarchical clustering. We also have a different technique for finding optimal number of clusters for k-means clustering. We will see once we reach there. We were discussing about iris dataset. So this iris dataset has 4 features, and and there are 2 attributes of this flower, sepal and petal, and we computed 4 features. And using this iris dataset, we'll try to cluster the different types of flowers. It has 3 different types of or 3 variants of iris flower, and each variant has 50 samples. So first, let's copy these data sets, which we will use in this tutorial, and try to import it into a galaxy. I have already imported them just to save time. People who are not sure how to do that, we just go to upload dataset, and then go to paste and fetch, and then we try to use them and then start. This will import all the 3 files. This file contains iris dataset, and there are 2 more datasets which we'll be using at the end of the tutorial. Let's first rename these datasets so that it's more meaningful. It's also important to see these files need to have CSV data types. Means it's a comma separated tabular file. Continuing the tutorial, we can we rename these data sets, and we already checked that all these data sets have CSV data types. And then we move. Here in this figure 6, we can see there are 3 different species or variants of this flower, and each of these flower has 50 samples each. We have 2 features, actually 4 features: petal length, petal width, sepal length, and sepal width. And based on that, we will cluster. This shows the dendrogram of the whole data set. Let's move on to the actual clustering technique. It's the numerical clustering tool, which defines many different variants of clustering. We try to search for numeric clustering, and then here in the hint section, you can see, please find numerical clustering in the statistics section. We go to the statistics section. Okay. And then here we find this tool. We just click on it. If you have some issues finding the tools, then one way to avoid that, this tool can be added as favorites, which I've already done. Then if you add as favorites, and then what you can do, if you click on show favorites, then these tools will appear, whichever tools you have added as favorites, so which will save your time in searching for the tools and go to the tutorial in a short amount of time. Let's select the iris dataset as a tabular dataset. This dataset contains header, so we can see in this dataset we have these headers. That for the headers, we can choose this help here and try to search for them, and then we try to the header name, which species. So we also have species defined inside header, but we are actually excluding them and using only the 4 features. We want to use hierarchical clustering, which we have already set, and number of clusters should be 2, and the Euclidean distance measure, and the linkage. Linkage here is as I said before, a linkage is actually gives you the minimization function of the distance measure that we are choosing here. So if you choose WOD, it actually minimizes the within cluster variances for each cluster. There are different types, like complete, average, and single. Here we are using WOD. And then we can run this. While it's running, if there are more questions or anything you didn't understand, I can try to explain again. Prem?
Yeah. So there is one question about the dendrograms. So this one is from Ramesh. So if I understood well, the bottom part of the dendrograms are subnodes that lie in the peripheral part, as explained in one of the slides.
So so at the bottom of each dendrogram is the number of samples, is all the samples that we have in our data set. And these are arranged based on the distances. For example, 9 and 23 in this example is the shortest distance, which can be merged together. And then this merged cluster can again be merged with 17. And there could be different clusters here which could be merged based on the distance. And by merging all these clusters, which are the next closest, we actually reach to the top, and one big cluster is formed. I hope I answered this question.
Well, Ramesh, if you have any follow-up question, please post it in the question box. Maybe you can also answer, if you still have time, If not,
Mhm.
we can
I
continue.
guess the job is still running, so
Okay.
I guess the job is still running. So so I
Yeah.
can answer this question if you have any.
Okay. There is another one from Kavita.
Mhm.
So it's about the evaluation of the clustering algorithm. So it is uh, it is easy to calculate accuracy of any model based on training and test data. But
Mhm.
how could I calculate the accuracy of clustering? Or I think in this case, unsupervised clustering algorithm when you
Uh,
don't
yes.
have any test data.
Um, yeah, I can try to explain it, which I would have anyways, because it's there in further in the tutorial. How do we evaluate clustering results? There is a section in the tutorial. Yes, with unsupervised learning, we are dealing with data. We have no targets. We don't know. We do not have the ground truths. So how do we do that? To solve this problem, there is a technique called Silhouette coefficient. By computing this Silhouette coefficient for the clusters, then we can evaluate these clusters. Higher this coefficient, better is our clusters. It tries to compute how close or how compact each cluster is and how different they are from each other or how distant they are from each other. If both of these criteria are met, then Silhouette coefficient for the entire clustering would be higher. Otherwise, it would be very small number. This is one technique which is used.
Okay, thank you, Anup. At this point, we don't have any new questions.
Okay.
So
Um,
I just remind everybody, if you have any questions, there is a question box in the control panel. Please post any questions that you have, and will and Anup and his colleagues will try to answer them as accurately as possible.
Thanks, Prem. We saw our data got computed. Now we can rename this data set so that we remember which is what. And here we just computed hierarchical clusters. Then we just name is as hierarchical clustering and then just save it. If you look at this tabular data, this is the same data what we had in Iris dataset. Just one more column got added, like the sixth column, which contains the cluster number. For example, the first few rows we see it's 1, and then maybe we find 0, which is actually the cluster number. So we have two clusters here, 0 and 1, labeled as 0 and 1. To visualize these clustering, we can use scatterplot tool in Galaxy. We will try to find here. There is a hint also for this tool. We can find it in the graph display data. We directly go to graph and display data, and we find a scatter plot with ggplot2. Again, to save time, I have already added this tool as a favorite. Then I just go to my favorite section, and then I click on ggplot2. Let's just plot this hierarchical clustering. We choose the data set in the first section, and since we can see here only 2 dimensions, we can just take only 2 columns. We cannot take, we actually clustered on 4 columns, but here we can take only 2 to showcase. So here we will take column number 1 here, and then column number 2, which is also described in the hands-on section. Then we can give a meaningful title to the plot, and then the X and Y axis names. Okay. We go to the advanced options, user defined plot of points, advanced options. We we are plotting multiple clusters in one plot. So we say we plot multiple groups on data point options. Also, we did user defined options. Distance as in multiple groups we already did. Now there is one attribute. It's column differentiating different groups. So this is the sixth column. Sixth number here refers to the sixth column that we actually learned after clustering, which gives us all the different clusters. We can use column number 6 here. Then we can also define different color schemes. And we also should define what should be the dimensions of our output image. For that, we can use output options. Define width of the output as 7 inches and height is as 5 inches, and depth for the DPI would be 175. Otherwise, the image is very large. And then we just execute this. Once this finishes, we can see the clustering of the data like shown in figure 6 or figure 8 of the tutorial. We can see there are two clusters here, orange and green, which defines one cluster. We can see two dimensions, the the sepal width, if it is higher and the sepal length is smaller, then it's cluster 1, and cluster 2 is with lower sepal width but higher sepal length. Here we also got finished. We just rename this plot as hierarchical let's just visualize this plot, which is similar to what we saw here. I'm sorry, it's just not fitting to my screen, so I just zoomed out. And we can see the same plot here. We have two clusters, and we used two dimensions. Next, we can talk about k-means clustering. As we discussed, k-means clustering actually tries to find the cluster centers. First, we randomly choose k centroids because k clusters need to be found, and all the data points are assigned to the nearest clusters and nearest clusters, and then with those data points inside each cluster, we try to take the mean and change the positions of the centroid, and then this process is iterated until we find convergence or the positions of the cluster centers stop changing. We can see this example in practice. We again go to the same tool. In our favorite, the tool is still there. Then we do the similar options and we choose the data set and we use exclusion option, and Here we use species. Sorry, we need to choose iris as data set here. And we choose species. And in in the clustering algorithm, we choose k-means. In the advanced options, we just need to set the number of clusters. So in the talk, I was discussing about how initialization of these centroids is very important. So here we use k-means plus plus, which is actually a better initialization technique, which which kind of guarantees that there is a speed up of convergence, and in the end we get good clusters. It tries to maintain distance between different cluster centroids, which are chosen randomly. We set up everything as a stable species and k-means, and then we just execute it. Okay. Meanwhile, I will try to explain how we can choose we can choose the right number of clusters for k-means. Inside k-means, we try to minimize the the variations inside each cluster. These variations, we can compute these variations along with the number of clusters, as we can see in figure 10. We can choose different clusters, different number of clusters, and we can choose within sum of squares inside each cluster, and then try to plot it. Whenever we see a bend in this plot for a particular number of clusters, then we can say that okay, even if we increase the number of clusters in a data set, then we may not gain something, and unnecessarily we may increase the time complexity of the algorithm. And then we can stop at this point and we say, okay, we have 4 number of clusters as the optimal number, and if we go beyond it, then it may not add much value. This is one of the ways we can define number of clusters for k-means. Let's see. Okay, our job got finished. We rename the data set as we did before. And to plot it, we again use the same plotting tool. And here we use k-means clustering. We use the first and second dimensions. We use k-means use axis. Then we choose the x and y axes, and then we go to advanced options. We use user-defined point options, 0, and we just want to plot multiple groups, and the column is the 6th one. And then we choose the coloring scheme. We go to output options. We set the height as 5 and as 175. And we just execute it. Also, there was one question about the running time of different algorithms. So hierarchical clustering, as I said before, the optimal version of hierarchical clustering has a quadratic runtime, is O of n square. while the Lloyd's variant of k-means is actually linear in terms of number of samples. Its complexity is O of nkdi. N is the number of data points, number of samples. K is the number of clusters. That's why to keep the complexity low, we should specify less number of clusters for k-means. And D is the data point dimensions. This is also one important point. If we have a very high dimensional data, then k-means may suffer from this. In order to find a remedy, we should use some dimensionality reduction schemes like PCA, and then reduce the dimensions to the most important ones, and then apply k-means on that. And I is the number of iterations. It's an iterative algorithm, so I gives the number of iterations. Higher the number of iterations, longer the program runs. We can check our job. Our job got finished. We can rename this plot. And we covered these section, and there are a few things about differences between k-means and hierarchical clustering. One is the time complexity. We already discussed that. And k-means actually works very well when our cluster is actually spherical or circular in shape. It actually suffers if the cluster shape is irregular in geometry. K-means also requires how many clusters do we need, how many clusters, and to define how many clusters, we need to do some pre-analysis before to find the optimal number of clusters for k-means. At this point, do we have any question, Prem?
Yeah, there are a couple of questions.
Yeah.
So this is from Ryan. Is there any similarity between k nearest neighbor classifier we used in classification and k-means clustering, since they both depend on distance?
The basic difference would be in k nearest neighbor classifier, we actually know the classes, but in k-means, we do not have any knowledge about the classes or the target. We just cluster based on the similarity. I guess on top of my head, I can think of only this answer. I mean, if I find any other answer, I will surely write it in the public channel.
So there is another one, and another question, and this refers to the Galaxy platform. Is there a specific tool in Galaxy to find the number of clusters for a given data?
Currently, I don't think so. Currently, I don't think so, but we may plan to include this kind of analysis tools. Anything else?
Yeah, there is one. So this is specifically referring to the plot that you show about the iris dataset, the hierarchical clustering. So there was supposed to be four factors. So the sepal length, sepal width, and petal length and width. And on that plot, we see only two factors. I think it was the scatter plot rather than the
scatter plot. Okay, this one. Fine.
So yes, I think it was this one. Yes.
Okay. So yes, in the original data, we have 4 dimensions or 4 features, but actually we cannot show all these features because we have only 2 dimensions. So we can show only 2 dimensions. That's why we took the first 2 dimensions and showed based on first 2 dimensions how our clustering looks, because we just can't show them the other 4 dimensions, the other 2 dimensions.
Yeah, I think that answers the question.
Yeah.
I don't think there are any more questions at the moment.
Okay. Okay. The scatter plot. So coming back to the tutorial, the scatter plot of k-means clustering looks something like this. So here it's more or less similar to the hierarchical clustering, but here if you see there are some region here which has overlapping samples here, and it's not able to distinguish which clusters it should go. So this region, yeah, is not so great, I would say. After these 2 clustering, the last clustering technique is DBSCAN, which we discussed. It tries to find clusters based on the density of core samples. Core sample, I'll try to explain again. A core sample is a sample which needs to have at least n number of samples within m distance. The n and m are the 2 hyperparameters of DBSCAN clustering algorithm. The the non-core samples can also be a part of the cluster, but it needs to be within m distance of a core sample. If it is beyond m distance of a core sample, it is considered as an outlier. Let's just repeat what we did, but with DBSCAN clustering algorithm. We just choose iris data set, and we just take all, exclude actual species name, and we just specify DBSCAN. So here we are running DBSCAN based on default parameters. However, if you look at, there are a few metrics which can be defined. The 2 metrics that I already discussed before, the M and N. N is M is actually the maximum neighborhood distance. This is also called EPS here. This is the maximum distance between 2 samples for them to be considered in the same neighborhood or same cluster. And this is the minimum number of points for a sample to be a core sample. If it needs to have 5 points within a distance of 0.5. With these parameters, we can run our DBSCAN clustering algorithm. We already discussed that. And okay, as this program is running, we can discuss the further data sets that we had already imported, the moon and circles data sets. These are 2 just randomly generated data sets using scikit-learn methods. Both of these data sets have only 2 dimensions, x and y, which is easier to visualize. And we will see how we can apply clustering on multiple data sets using these 2. Okay, so our clustering got finished. We just give it a meaningful name. And then we do the scatter plotting, and we again do the same procedure again, and we can give a meaningful title to the plot, and go to advanced options, and we choose user point of view. We want to plot multiple groups, and sixth column defines the cluster types. Then we choose the coloring scheme again, and then we define the plot dimensions. These plot dimensions are not fixed. You can change these dimensions as you wish. As I was discussing about the moon and circles datasets, let's just have a look at these datasets. As I said, there are only two dimensions, X and Y. And these are randomly generated datasets using scikit-learn methods for experimental purposes of our learning. So these two another data sets, we can just show an example how to use multiple data sets for clustering at the same time. Let's just rename this plot. Then we see a scatter plot based on so here we again have a similar clustering visual, but there is a difference here. As we were discussing that the non-core samples which do not fall within the threshold, and they are considered as outliers. We can see those outliers as the green points, which are marked as -1. These are actually termed as outliers by DBSCAN algorithm, which are not falling within a certain distance of the nearest core sample. You can see those, and other clustering remains more or less similar. Okay. So here we see that these green points, which are marked in the legend as -1, are not contained within any cluster, and they are considered as outliers. Therefore, DBSCAN algorithm is actually very good at handling outliers. And also, we do not need to specify the number of clusters it needs to find or needs to have. It can do on its own. Let's just move to another section, applying multiple data sets to the clustering algorithms. Before that, let's just visualize these data sets. To visualize, we again use the scatterplot tool, but this time we'll use multiple dataset options. And in these multiple datasets, we use the datasets we actually imported, the moon and circles, and we can select it like this together. And then since we have only two columns to plot, so we can give this as scatter plot, and we have labels as X and Y here. And then we can specify the dimensions of the plot as before. And then we just plot these data sets as such to see how do that look like. In the tutorial, we can already see on the left, this is the circles data set. We have two dimensions, X and Y, and on the right, we have moon data set. having the same two dimensions, X and Y. We need to find uh, clusters inside these two data sets and see how these different clustering algorithms differ in computing the clusters. Okay. So since these plotting tools are still running, we can actually in parallel we can run these clustering on them, which will be running separately. Okay. Again, we will choose two both the data sets, and data sets have headers. Yes. Now we do not have any any other columns which we are not using for clustering. Therefore, we will use all columns in this section because we are using both the dimensions present in both the data sets. Now we use this hierarchical clustering, and in the advanced options, we will use a number of clusters too, and the same options, and we just execute them. This job will give me two files and corresponding to both the data sets, and we will have clustering information in both the data sets. So while it is actually yellow, we can actually rename these data sets, but we are here not sure if the first one belongs to Moon dataset or to Circles dataset. To find that, we can go to the information of this job, this eye icon. We can go here and we can see in the details, input parameter, we see the input dataset for this job is Moon dataset. We know that this is running for Moon dataset. Therefore, we go to renaming option and we select the right dataset name, and we just rename it, and we do the same for the other job as well, and this belongs to Circle. So for this as well, we can go to the information and we see this is running for Circles dataset. Now we have renamed everything, and the Moon dataset got finished, or both of them got finished now, and we can see the output of these datasets. We started with only two dimensions, and now we can see we have the third dimension also, which gives the clustering information. Similar is for the Circles dataset as well. Now we can visualize the clusters using the same scatterplot tool. We go to scatterplot tool and we again use multiple data sets, and we use Moon and this clusters information, and we have only two dimensions to plot, 1 and 2. We can give hierarchical clustering as the plot title, and X and Y labels. In advanced options, we have find we want to give multiple groups, and here we saw that the third dimension has added the cluster information. Previously we were using the sixth dimension, and now we will use the third column or third feature. We should be careful about the number, the feature index that we are adding here, so that our plot in the end is right. Then we choose the color scheme. and then we specify the dimensions of it, not 175. Now we just execute it. This will again give us two files, one for the moon dataset and one for circles dataset. We can rename them as we like. Now, for both these datasets, we ran hierarchical clustering, and we can actually run k-means and DBSCAN as well on both of these datasets. That's a task for the participants. They can try these things on their own, and in the end, we can actually compare these three algorithms on the same datasets. Here in figure 13, we can see on circles dataset how the clusters are actually computed. In DBSCAN clustering, we can think about how it creates the clusters. We discussed that it creates clusters based on density. Here we can see this whole region has has core samples defined, and therefore this whole region becomes one cluster. And similar is true for this outside ring, which is another dense region. But for k-means, it's different. It actually depends on which points were chosen as cluster centroids in the beginning. Looking at the clustering, we can assume that the cluster centroid could be here for the green clusters, and for the orange cluster it could be here. Similar is the case with the moon dataset as well. The cluster centroid could be here for k-means, and for orange points and for the green points could be here. Again, a similar explanation can be given for DBSCAN. This is one dense region which were clustered together and as orange point, and this got clustered together as green points, which gives two dense regions in the moon data set. We can see the output. This is for the moon data set for hierarchical clustering, and we can see the output here as well. And for the circles data set, you can see output with two clusters, which is this one. We can run the same algorithms which we discussed before, k-means and DBSCAN on these two data sets, and try to find the same clusters. In conclusion, we can say that these different clustering algorithms have different techniques to find these similar samples. Therefore, it's very important to know the data set, what kind of data sets we have, what kind of clusters we can assume, or how many clusters we need to have, or we can have. This kind of analysis should be done before choosing a clustering algorithm, or we can try out different clustering algorithms to see which one works best to our assumptions. Also, it's very important to optimize the parameters. There are different hyperparameters of these clustering algorithms, and it's very important to optimize those because they vary from data set to data set. I think I am done with the talk and demonstration.